example where invariance will help us. It's not going to be the entire thing like in that last example, but it will help us to simplify the situation and allow us to solve the game. This comes from one of the exercises. I believe it's number 16 in section 3.7 or 9.7 in the book. It's called Drescher's Guessing Game. Player 1 writes down one of the numbers 1 through n. Player 2 will repeatedly guess what player 1's number is until she guesses correctly, losing 1 for each guess. After each guess, player 1 must say whether the guess is correct, too high, or too low. Solve the game for n equals 3. So in order to start to analyze this game, and we'll be talking only about the n equals 3 case, we have to understand what the pure strategies are for each of the players. This can be a little tricky even in a situation like this. Player 1 picks a number 1, 2, or 3. Those are the pure strategies for player 1. 3 possibilities. But for player 2, a strategy means how player 2 will play the game. It's not just picking a number, it's defining a sequence of picks. So here are some examples. Player 2 can have a strategy that says, I'm going to try to pick 2 first, and then of course 1 will tell me whether my guess is correct, too high or too low, and if it was too high or too low, I'll then know what the correct answer is, and then I'll pick the choice that's indicated by player 1's response. So I'll just call this the pick 2 first strategy and do the right thing. But she also could make other choices, like she might say, I'll pick 2 first, and then if it's wrong, I'll do something stupid, and if I'm told that my guess is too high, I'll pick 3. It'll be wrong, but that's something I could do. So I'll just call this the pick 2 first and be stupid strategy. Those are legitimate strategies that player 2 could pick. What are other strategies? Well, player 2 might begin by choosing 1, and then of course we know if that's not correct, that the next will have to be higher, so maybe the strategy is choose 1, then if necessary, choose 2 next, and then of course if that's still wrong, choose 3. So that's another pure strategy. Another pure strategy is to pick 3 first, then of course if that's incorrect, that has to be too high, so then pick 2 next, then pick 1. Another possibility is to pick 1 first. If 1 is wrong, you know that 1 is too low, so pick 3 next, then 2. Or maybe pick 3 first and then pick 1 next and then 2. And you'll see that these are kind of all the possibilities that make any sense at all, but there are other possibilities which I won't even list, which actually make this not a finite game, where player 2 could just pick 1, and if it's wrong, player 2 could pick 1 again, and then 1 again, and then 1 again. That would be a stupid thing to do. So if we ignore situations where a player just repeats a pick that she already knows is wrong, these are really the only 6, I think it ends up being 6 pure strategies that make any sense whatsoever, and even among these, we've indicated one of them still doesn't make any sense, but we'll see how that comes out in the wash. Let's look at the matrix for this game. We can see here for player 1, the choice of pure strategies were just pick that number secretly, 1, 2, or 3, and I believe this was the pick 2 first, and then do the right thing, which means pick 2 first. So if 2 happens to be right, that the payment is just 1, that's the number of guesses. If 2 is wrong, player 1 will tell whether 2 was too high or too low, and either way then player 2 will be able to pick the correct one. So there will be only 2 guesses in either situation where player 1 has picked 1 or picked 3. If you have the 2 first and be stupid, then again it will be a payout of 1 if 2 was correct, but then a payout of 3 if it wasn't 2, because if it was 1, player 2 would have picked 3 next and then 1, and vice versa if it was 3. And then here are the other choices. I forgot the order of these. The next one was choose 1 first, then 2, then 3. So if the player chooses 1 first, then 2, then 3, it'll be a payout of only one guess if it's 1, 2 comes second, so payout of 2 if it's 2, and 3 comes third, so a payout of 3 if it's 3. I'll call this the 1-2-3. This one, of course, is the 3-2-1. Pick 3 first, and if it's wrong, pick the 2 and the 1. And then, of course, these are the others, the 1-3-2 strategy, and this is the, I'm sorry, that's not correct. No, that's correct. Pick the 1-3-2, and this is pick the 3-1-2 strategy there. So these represent the 3 strategies that kind of make sense. Now we have a 3-by-6 game. Column 2 is clearly dominated by column 1. You could guess that from the name. Column 2 is the pick 2 first and be stupid. That's not as good as picking 2 first, paying attention to what player 1 says and picking the correct number. So it's dominated. You can see that from what our normal definition of dominated is. The 2 is less than the 3 here. So we can just eliminate that column entirely. And then we'll notice the following thing. The 1 and the 3 play a very much symmetric role in this game. So I claim that a transformation that just replaces 1 by 3 and 3 by 1 for both players gives us essentially the exact same game. And you can check that yourself if you just think of interchanging 1 and 3 for both players. Everything plays the same under all situations. And what does that mean? That means there are optimal strategies for both players in which, there are optimal strategies for both players which are invariant under transformations that switch 1 and 3. That's kind of the same as saying the 1 and 3 will have equal probabilities in some optimal strategies for both player 1 and player 3. So how does that help us here? Well, it means instead of having player 1 use a strategy of picking 1, that's one pure strategy, or picking 3, that's another pure strategy, player 1 can replace that, if we're looking just for optimal strategies, by one which uses 1 half the time and 3 half the time, since we know in some optimal strategy they'll be picked with equal probability. So instead of having the choices be 1, 2, or 3 for player 1, I'll label this first row here 1 star, and the second row 2, where 1 star is what probability 1 half, or say pick 1 with probability 1 half, and 3 with probability 1 half. Row 2 here just represents picking a 2. But row 1 now will be pick a 1 or a 3, half the time either one. Similarly, because 2 will have an optimal strategy which is invariant under switching around 1 and 3, we can see that this 1, 2, and 3, the 1 first, then 2, then 3, and the 3, then 2, then 1, can be replaced by a strategy, which will go here, which says make a choice of the first thing to pick, which is half the time 1, half the time 3, and pick 2 second, and pick the other 1, 1 or 3 third. So kind of a combination which is 50% this column and 50% this column we can use for this column here. So let's call let me label these columns. I'll call column A here the choice for player 2 that says pick 2 first and be smart about it. That's not going to be changed by invariance. But I'll call this column B is pick with a half probability of 1 half, pick a 1 first, then 2, then let me start that again. Pick with a probability of 1 half of 1 first, a probability of 1 half that the 3 is first. Then we pick 2 second, then pick the other one third. And what do I mean by the other one? Whichever one you didn't pick to begin with. So that's the strategy by column 3. And what are the payouts? Well, column 3 had column B here represented an average of these two columns, and the average payout in these two columns was 2, 2, and 2. And then, of course, player 1 averaged the first and last one. They end up being 2 and 2. 2 if player 1 plays the 1-star strategy, and 2 if player 1 picked 2. And finally, look at these last two columns. They represent the pick 1 first, then pick 3, then pick 2, or pick 3 first, then pick 1, then pick 2. What I'll call column C, then, is an average of 1/2 times this column plus 1/2 times that column. In other words, pick with probability 1/2 the 1 first, and with probability of 1/2 the 3 first, then pick the other one in the second position, and then pick 2 last. And what are the payouts? What are the payouts here if player 2 uses strategy C here, which is the average of these two strategies? Well, you can see the average of 1 and 2 is 3/2. The average of 3 and 3 is 3. The average of the 2 and 1 is 3/2. And remember, 1 is playing the average of those two. So that's why we get the 3/2 in that position. So the game has been reduced from this 3x6 game to this 2x3 game, which is much simpler. And furthermore, a really nice thing is that you can see column B is dominated, I should say, by column A, because we have 2s in both positions here in row 1-star, but we have a 1 here and a 2 here. So we can just eliminate column B, and we end up with columns A and C, and choices 1-star and 2-star here. Let me rewrite that here. We have columns 1-star, not 2-star. I said that incorrectly, just row 2. There's row 1-star and row 2, and this was choice A and choice C. Now this game is easy to solve. It's a 2x2 game. We've done that several times already. There's no saddle points, so equalizing strategies work, and we have formulas for those, so I'll just tell you the end result. We can use the formula for the value of the game, which says it's going to be the determinant, which is 2 times 3 minus 3/2. That's 6 minus 3/2 and 9/2, and divide that by 2 minus 3/2 plus 3 minus 1, which is 5/2, and 9/2 divided by 5/2 here is exactly 9/5 there. We can then again apply the formulas for the optimal mix strategies. For player 1, it would be 4/5, that's for row 1-star. 1/5 is for row 2, and for player 2, it would be 3/5 for choice A and 2/5 for choice B. Now, how does that translate into the original game? Remember, 1-star was half the time play 1 and half the time play 3. So what does that mean for our original P in the original game? To find an optimal probability vector P. Well, this 4/5 for 1-star meant a 2/5 to pick a 1 and a 2/5 to pick a 3. This was from the invariance. 1-star meant pick either 1 or 3, each with probability 1/2, and we do that 4/5 of the time, and the 2 gets picked 1/5 of the time. What about for player 2? This is for player 1. Yeah. For player 2, we have these two strategies here, A and B. Strategy A is the pick 2 first, and then play correctly. And I'm sorry, that shouldn't have been B. That should have been, let me change this, A and C. That was row C here. And if we go back and remind ourselves what C represented, C was pick half the time, pick 1 first, half the time, pick 3 first, then pick the other one, then pick 2 last. So 2/5 of the time we'll do that, which means 1/5 of the time we pick 1 first. I'll just write it like this: 1 first, then 3, then 2. And 1/5 of the time we pick 3 first, then 1, than 2. So these are the optimal strategies, and you'll see because of the invariance, these of course are the same. We just split them from the 2/5 and split them from the 4/5. These two are the same. Invariance really helped us simplify the strategies a lot, to the point where we could get a game matrix that was easy to solve. Try to make sense of this and see that it makes sense that player 1 should play 2 rather infrequently, and player 2 has a large incentive to pick 2 first, because that makes the total number of guesses smaller in many situations, and when not picking 2 first, to use these other strategies.